My name is Fred Kim. I'm an engineering consultant at HBM Francia, formerly known as nCode. And there's also the name of my colleague Thomas Kemmerich from the German office, and I'd like to acknowledge here his help to build this presentation. So I hope you can hear me fine. So this webinar is about rotating machinery analysis in nCode VibeSys. And I'm personally in charge of promoting VibeSys, and rotating machinery is part of this of the capabilities of this software. So let me just introduce you very quickly. Sorry for this commercial bit, but I'd like to introduce you very quickly the various softwares that we HBM Francia are editing. So we've got, at least on the nCode side, we've got Design Life for FE-based fatigue analysis. So basically, you end up with a contour plot of damage or life from existing stress calculations. We've got GlyphWorks, which is a very famous software of ours for signal processing, general purpose signal processing, and it's very dedicated to durability type applications. So strain gauge, if you like, signal processing, and fatigue analysis, fatigue damage, damage editing, you know, what in the signal is generating damage, things like that. We've got automation, which in here we've got a database like Oracle, and the idea here is really to have dashboards and giving you gold information, so you no longer look at the waveforms of billions of data points, but you just have a very summarized table with just what you need in terms of trends and global statistics. So that's automation. And here's VibeSys. So VibeSys is the latest software. It's 1 year old now, and it's very similar to GlyphWorks. And basically, this one VibeSys is dedicated to acoustic and vibration analysis. So it works exactly as GlyphWorks or Design Life work. In other words, it's using, we'll see that, you know, pre-configured analysis. We call them glyphs, and therefore you can build your process very easily and reuse it over and over again. So let me just briefly introduce you to VibeSys and especially its key features. So today we're gonna see what we have in terms of rotating machinery. So that means waterfall analysis, order extractions, Campbell plots, etc. So we'll cover that today. But also in VibeSys, be aware we've got human perception analysis. So that means, you know, how the human body reacts to sounds and vibration. So that means comfort and things like that. We've got structural dynamics. In other words, model analysis. So we can extract model parameters to FRF curve fittings, animation as well, operating deflected shapes. Either, you know, you can animate that a wireframe, you know, simplified geometrical structure, or a whole FE model based on measured data. We also have a vibration manager, so that's a database which contains a series of spectra from various standards, but you can add your own spectra in there, and you can use them to compare you know, with your measured data, for instance, or compare between all the spectra from the various standards and pick maybe the envelope spectrum or something like that. So, and in terms of the benefits of VibeSys is also the fact that it can analyze, you know, huge time series. It's really meant for that. So there's no limit in terms of the number of channels or the number of data points per channel or the sample rate. And the idea is, you know, it's process oriented. So the idea is you build your analysis graphically, and you save it. You can share it and use it the next day. In terms of functionality, so we covered the main families of applications, but we've got like 100 different algorithms in there. So you can mix and match all those glyphs and create your own analysis. And if by any chance you don't find the analysis you are after, or if you are part of a research department or something like that, you could code your own analysis, your own algorithm using Python or MATLAB, and therefore create your own little box like this one that does signal processing. So let's start the topic of today. So that's the analysis of rotating machinery. So we find rotating machinery pretty much everywhere. Everywhere you've got a pump, a turbine, an engine, generators, etc., etc. You've got something that rotates, and therefore that is likely to create vibrations. So what's happening typically is if you've got a problem of imbalance, for instance, you've got one burst of energy, of vibrational energy at every revolution. Other phenomena appear twice per revolution. For instance, if we take your car's engine, say it's a four-stroke, 4 cylinders thermal engine, say, you've got 2 sets of explosions per revolution of the crankshaft. So you've got some phenomena, some vibration phenomena appearing twice per revolution. So everything would be easy if the speed was constant, but unfortunately it's not. So we've got fluctuations in speed, runs up, goes down. Sort of the speed may as well move, change it in time, and therefore the frequency content changes as well with time. So we have to really understanding what vibration is directly linked with the main shaft or a shaft, say, and how is it linked? Is it occurring at each rotation or at so many multiples of rotation, so which we call harmonics. So basically here we are considering measured data. So you've got sensors, typically accelerometers, but there's nothing stopping you from using strain gauges, microphones, any sort of sensor that's able to capture the vibrations and the mechanical phenomena that are resulting from an operating engine or component, right? And we'll see that we need also another input we need for this type of analysis is the RPM profile. And why would we want to do a rotating machinery analysis? So first is probably to monitor and you assess the levels of vibration which may cause damage. So you're recording the signal and you look at various metrics, and if these move with time, something's bound to occur. Another big application, which is, everything's related really, but the other application is determine what the critical speeds are. In other words, a speed that corresponds or that is exciting some resonance frequency of some component that sits on the top of the engine, for instance. So you want to avoid exciting those modes because this generates noise, fatigue damage, and discomfort and things like that. So you want to make sure that your orders, we'll see that later, do not cross resonances. Also, it's very useful to do fault diagnostics. So I mentioned it before, the misalignment, the unbalancing, or defects in gears, in bearings, etc. So we can see that we can see the signature, if you like, of that in the signal, and we have a series of analysis within VibeSys that enable you to find out that that's a defect I'm now seeing in my data. You can point to the defect and you can tell how bad this defect is. And finally, another nice application is sort of the signature analysis. So you've got say something that happens 11 times the fundamental frequency or the rotating frequency of your main shaft, and you realize, for instance, that there's a fan with 11 blades that runs at the same speed of this shaft, or you can by this type of analysis you can find out which part of the system is generating that noise. So the first thing that we need to make sure we have for this analysis is the RPM signal. So the speed, in other words, the speed of the shaft versus time. So typically, this speed is obtained by a measurement using a key phaser or a probe, and this one typically generates pulses every time it detects that there is a revolution. So that there may be as well several pulses per revolution. In this very simplistic example, there would be one per revolution. And what typically happens is you want to know the delta time, between pulses, and knowing how many pulses you've got per revolution, you can therefore deduce the speed. So in other words, how many revolutions per second does my shaft rotate at? Sometimes, measurement is never perfect. You may have pulses that are missing, and in some other time, you can have spikes that occur and that are not pulses. So when calculating the delta time between pulses, you have to take into account those possible anomalies. So I'll then do a demo, and we'll have an example pulse signal, which will convert into an RPM signal. So I'll show you how this can work in practice. But basically, yes, we need definitely to have this RPM signal. Once we have this RPM signal, so it is represented here in this slide in red. So you see revolutions per minute versus time. So these are time series, right? And that's typically a run-up where the speed of the shaft increases with time monotonically, and in parallel to that, you've got some vibration signal, right? So the idea is to do a series of spectral analysis for various speeds. Let's start, for instance, by considering the speed of 3,000 RPM, for instance. So that's 3,000 RPM. Around 3,000 RPM, this is the corresponding signal, in this rectangle. We could extract this signal, cover this signal with buffers, just like, the usual FFT type analysis. So you've got a number of buffers, each with a given length or buffer size. They are overlapped with a given overlap in person, for instance, and they are also windowed, like Hanning or those type of windows to avoid leakage, right? And therefore, out of these 6 buffers in this example here, you can derive the spectrum of the response signal around 3,000 RPM. So let's see in practice how it works. Take this RPM signal that's constantly increasing. The user, in other words, when you're using the software, you have to give it a minimum speed you want to consider, a maximum speed, and how many of these spectra you want in between. So let's do a first spectrum. So let's center it around 3,000 RPM. So this is the signal that I want to extract. I cover it with buffers, each having a length, a given window, overlap, etc. And this enables me to eventually, get this spectrum, which I'll represent next to the corresponding RPM value. Then we continue. We go to a higher RPM value, so to 3,500, say. So that's a new signal I wanna isolate, and I want again to do some FFT analysis and extract the PSD or the modulus of the FFT or whatever, and display it again next to the new RPM. And let's continue till we covered our range of speeds, right? So that's the third spectrum I'm obtaining, etc., etc., till you eventually obtain this waterfall color plot, color map, if you like, showing you the frequency content, so that's the frequency in hertz, right, versus the engine speed. And what we see are those lines, which are linear, and that show us that the vibration content is proportional to the engine speed. And the slope of those lines indicate the harmonic number, right? So we expect, again, for a four-stroke engine to have a line at twice the speed of the crankshaft. Plus, it's harmonics, because it's never a perfect sine. It's an explosion, so it's a burst, and you'll have loads of harmonics. So we expect the fourth order, etc. So I guess you're all familiar with that. Now let's just recall, because recently we had quite a few. As I said, VibeSys is quite new, so we're trying to make this software known and renowned for vibration analysis, and we get more and more users, so we're very happy about that, and therefore we're getting also support requests, and we realized that sometimes there are some fairly basic things that are not necessarily fully understood. So, for instance, those spectra that I just mentioned before have a given frequency resolution that I'm going to call here delta F. And delta F is actually calculated from the sample rate of the original signal. So generally, there's little you can do about that. That's the sample rate of the signal. And the buffer size, so that's a user selectable property. You can choose various buffer sizes. And therefore, if you go with a high or long buffer, high buffer size, you'll get a smaller delta F, right? Smaller resolution. So that's quite nice in a spectrum to identify what's the exact frequency, or to have better, a more accurate, if you like, estimate of the frequency at which occurs a given peak, for instance. But on the other hand, this spectrum is quite noisy. So you may want to use a shorter buffer. So if those are PSDs, whether you use a long or short buffer, normally the spectral RMS should be the same. The difference here with a shorter buffer, so a larger resolution, is you won't have a very precise reading of your frequency, but it's less noisy, therefore gives you a trend, if you like, a tendency, as opposed to something that's very peaky and noisy. So it's up to you. Now that's for a global spectrum. That's valid for a global spectrum. When we're talking doing a window spectrum, in other words, like we are covering a range of RPMs and obtaining a spectrum every 100 RPM or something. What we need to keep in mind also is the fact that a very long buffer size, which gives you a very fine resolution, right? The problem with long buffer size is that they produce what's called smearing or the blurring in speed, because that's the speed axis. So if you consider a very large buffer, it'll cover a range of speed. The speed can't be assumed to be constant throughout this buffer because it's very large, and therefore, instead of having one peak at a specific frequency, this peak will be smeared, and you'll have a wider peak, right? Because the frequencies are swept because the buffer is too large. So you may want to go to a smaller buffer. So it's always, it's the famous uncertainty principle. You can't have both a nice resolution in frequency and a nice resolution in speed. You have to choose, or you have to find a compromise. So I'm afraid there is no general rule. It depends on what machine we're talking, which speeds are involved, how many harmonics you're interested in. It depends on a lot of things: buffer size, the sample rate, etc., frequency content, etc. So I guess it's it's up to you to choose which buffer size is best for you. Now, in terms of displaying those waterfalls, we've got another way of displaying those color maps. It's called a Campbell display. It makes it somewhat clearer sometimes. So you've got a cutoff below which the display stays white, right? and above that cutoff, depending on the energy, so that's the axis that's perpendicular to your screen, you've got those circles, which the diameter depends on the energy, right? So you can see orders sometimes, in a clearer fashion, and you can put those order lines, or on the top of them. So that's second order, fourth order, sixth order. You can also, in this Campbell plot, I'll show you later, but it's interesting to also display those vertical lines which represent specific resonances, for instance, when the when the order is obviously crossing a reference, because you've got all of a sudden a big energy there, and then also you have horizontal lines that you can position on this spectrum, on this Campbell plot. So it's quite an interesting one. And also, if you happen to have a non-linear phenomena in there, we can enter sections of curves, multi-point curves like that to track the non-linearities and compare that with some theory or whatever, So that's quite an interesting display. Now, in terms of those Campbell or waterfall plots, what's interesting is therefore to not only identify the various orders, but also to extract the order slice. So the idea is to put a cursor, for instance, on order 2 and order 4 and order 6, and extract its amplitude versus RPM and compare them, and see that in this RPM range, it's order 2 that dominates. In the higher range, it's order 6 or whatever that dominates. So in order to do this, we've got several solutions. You can do that within the waterfall display. I'll show it to you later. But the best thing to do, and I really like to insist on that today, is to use a dedicated glyph. It's got a complicated name, I agree, but it's very useful. It's called complex frequency manipulation. So this one enables you to extract an order, as you can see in the property window displayed there. So you enter here the value of the order you're interested in, and also it's got a bandwidth around that order where you can sum all the energy, and the output is a very smooth, or can be smooth order slice. And you can do that for order 2, 4, 6, whatever order you like. And also this one's capable of extracting what we call the overall spectrum. And typically, not only do we overlay the second order and the fourth order, etc., and compare them, but typically we would put on top of them also the overall spectrum. So that's the total energy we see from, across the range of RPMs. So it's a spectrum, just like an order slice, but it's it's much higher, and you can therefore tell which order contributes most to the overall energy at that RPM. So we'll see in a minute how to do that during a demo. Before doing so, I'd just like to, since we don't have the whole day for that. I'd just like to add additional capabilities that we won't have time to discuss here, but we've got an order tracking glyph, so that's for extracting the time domain waveform corresponding to a specific order, right? So you want to remove order 4 from your signal. So that's typically used for re-listening to the signal, sound quality without order n, or you could diminish it by a half of its power or something like that, So we can extract order specific, waveforms for specific orders. We can resample the data in the revolution domain. I don't know if that's big enough, but this signal displayed here in red, the x-axis is no longer time, but revolution domain, revolutions, right? Number of revolutions. So if you happen to choose a buffer size that corresponds to an integer number of revolutions, you get a leakage-free spectrum eventually, right? And also it's worth noting that you won't find any smearing. So leakage-free, smearing-free spectrum. So that's probably the best thing to do. So you end up with those waterfalls here with the x-axis is no longer the frequency, but it's the order number. So order 2 is a vertical line, order 4, 6, etc. And that's probably the most precise, the most the best way to extract order slices, I think. So we can do therefore order spectra, order waterfalls, order-based waterfalls. We've got also a very nice periodic display, especially once you've resampled your data into the revolution domain. So you can ask, for instance, I want to see, every revolution. I want you to display the signal corresponding to every revolution in an overlay mode. So you may as well find a plot like this one where all the curves overlay nicely, you see, and we've got running statistics that can extract the maximum envelope, the minimum envelope, the mean value, on a cycle-by-cycle basis. So that can be very interesting for, pressure fluctuation inside of a cylinder or things like that. Every phenomena that occurs at every revolution, and that's meant to be periodic. Yeah, especially for fault detection in bearings, we've got the envelope analysis. So that's taking the envelope of your vibration signal, and the idea is to do the FFT of the envelope signal. So that's called demodulation analysis. Similarly, we've got a Capstral analysis, so creating Capstra, so a spectrum of a spectrum, and that's when you've got a loads of harmonics, and typically due to that happens in gears. Whenever you get a fault in a gear, a tooth that has an issue, a fault, right? You've got harmonics that appear, and therefore, or you've got sideband frequencies, sorry, that appear, and that's typically it's becoming very clear in the Capstral domain, and also in terms of detecting faults, we've got the kurtosis as a statistical metric. So you could do the global kurtosis on your signal, or a running kurtosis. So every 10 seconds, every minute, say, on a signal, you calculate the kurtosis and see how this one evolves with time. So that's another metric that tells you whether something's going wrong, say, in your signal. So now I think it's time for a live demo of VibeSys. So let me just share VibeSys. So I hope you can see that now. So basically, that's the nCode desktop, right? And on the left-hand side, you see different buttons. You see the GlyphWorks button, Design Live button, and here we've got VibeSys below and others, right? Automation, etc. So I'm going to click on VibeSys. Those of you who are familiar with Design Live and GlyphWorks will not get lost at all. It's really the same interface. So we've got an available data window here with the data that sits in the working folder that I've picked when I started the software, and so we've got 2 tests here with 4 channels in this one, 2 channels this one, and on the other side of the screen we've got our library, if you like, of glyphs. So basic digital signal processing, data cleaning, structural dynamics, so that's modal analysis, right? Human perception, so that's rather acoustics and human body vibration. And here we are, rotating machinery. So we'll find a number of glyphs that we'll use now, and especially the pulse to speed, waterfall analysis, and complex frequency manipulation. So let me start first by showing you how this software works. Basically, for those of you who are not familiar with the software, I think it's very easy to use. It's just a matter of selecting, you know, with the shift or control button, the channels you want to process, or grab the whole test with it. It's 4 channels. You could even, once you've created an analysis here, drag the whole time series directory on the screen, and it'll process everything. So you can go from a very refined analysis to something that's large-scale automatic processing, right? So here I've just dragged the three acceleration channels, X, Y, and Z. So you can zoom in, overlay, and here you've got a toolbar that corresponds to this very XY display type plot, where you've got a series of capabilities, options, like to display in log axis and things like that. But here, what I want to do is just show you a very basic analysis. Let's make the global PSD, say the overall PSD of those signals. So here we've got frequency spectrum. This one sits in many palettes. You drag it on the screen just like you drag your signal. So you drag it on the screen, and it's a matter of playing Lego here. Sorry for mentioning a trademark here, but you just linking, you know, those 2 connectors together, and then you want to display the resulting spectrum. So you go into the palette that's called display, and we've got a series of different ways of displaying data. We'll see that we've got, for instance, the waterfall display, the Campbell, where is it? Campbell plot here. We've got means to display FE models, but here I'm interested in a spectrum X and Y axis. So the XY display is perfect for me. So I'll drag it onto the screen, and even better, I'll drag it straight onto the output connector. So I'm even saving the one button click, right? And that's pretty much it. You know, I can run now I can press now the run button here. And that's it. It's calculated the PSD by default of my signal. So I've got here 3 PSDs that I can display in log fashion, zoom in, etc. So why am I saying by default? Because indeed this glyph has many properties that you can access by double-clicking on it, and you can change that. You know, you can change the buffer size, etc. And the idea is this one. You know, you create your flow, your process, your analysis workflow by drag and drop, and then you save it. You save process. You call it Fred, for instance, and therefore you can reuse it. You know, anytime the next day you reuse it. It has saved the layout, the options, and it can be very complex. You can share that with your colleagues, etc. So it makes your life very easy, especially if you got repetitive actions to do. You know, but even though it's every day another day, and you've got other actions to do, it remains a very easy to use product. So let me just open up now the demo workflow I prepared for you. Now that you know how we build those analyses, I'm going to show you a couple of analyses that do series of processings, right? So here I'm using various tabs. You know, just like in Excel, where you've got different spreadsheets, here you can have different workspaces. So the first workspace is called pulse to speed. So I've got an example signal here that I'm dragging in there, where I've got my vibration signal in red and G, and in blue, what represents the speed is actually a series of almost pulses, right? So say there is one of these bursts, high excursions occurring per revolution. So what I want to do is use this pulse to speed glyph. The reason why I'm using a test splitter, I'm a big fan of test splitters, and I'll explain you why in a minute. So I've decided to use this test splitter and test combination because, you know, it enables me to not worry about which channel should I pick to do this very specific action. I can just drag the whole test with all its channels in the input glyph, and just let this glyph do the filtering. So in this one, I'm asking for the speed channel to be isolated, if you like. So the channel that has the channel title speed will be isolated. So it goes through this pipe. And in there, I've got all the other channels. So this one is the path. The channel contains channels that have passed the test, the condition. And this connector contains all the other channels. So in there, then we enter this glyph. So let me just press the run button. And here we recombine speed, the calculated RPM profile with the vibration data. So let's have a look. So that's the same vibration data. It hasn't changed whatsoever, not moved. And this is now my RPM profile. I notice it's very noisy, probably because this is a fairly low sample rate. Let me just right-click on there and select details. And indeed, the sample rate is quite low, 1,000 hertz. That's really the bare minimum you could do, and so it's difficult for the analysis for the glyph, to detect when the threshold is exactly. I guess that's probably an explanation of this noise when the threshold is exceeded. So by the way, where do I set all the threshold things and the algorithm? If I double-click on there, I've got a series of properties. One of them is called the trigger level. So that's where I'm telling it node 6, increasing. So every time the signal increases node 6, so therefore with the positive slopes, every time it increases node 6, that's the position in time of a pulse. And therefore the delta time will be calculated between each pulses. The output units is RPM, and I've got, say, 1 pulse per revolution. So now what I can do to improve this noisy RPM signal is just to perform a running average on the signal. So say every 3 points, I'm performing a running average filter over this signal, and every 3 points it averages. So let's run it again. Now it looks better. I could even smooth it further by going to 5 points. Yeah, it's much better now. So I've got my RPM increasing with time, and I will see in the next tab how we can perform a waterfall analysis with all the extractions, etc., from that signals, right? Last thing I wanted to say is in there, under advanced, that's where you've got the anomalies, the management of the anomalies in the pulse signal. For instance, we've got this error band. It's impossible that the speed varies 5% between pulses, right? If a pulse is following an next one, the previous one, and this delta time proves a variation of speed over 5% compared to the previous speed calculated, it's bound to be an error, or whatever percentage. By default, it's 5%. So because the speed can only vary at a given pace, the given slew rate, and not too fast. So that's one way to trap spurious spikes. And if this value is exceeded, well, this pulse will simply be ignored, and it goes to the next one. Also, the zero check. So if sometimes you've got missing pulses, and sometimes for a long time. So what should we do? Should the RPM profile drop to 0 suddenly? And what if one pulse is missing? So here we manage what happens if there is no spike over a period of time that you specify here. So it works well. It works really well, and pretty much every time we manage to get a smooth speed signal. So that was a big introduction. Let's now move towards the waterfall analysis. So now I'm going to use this second test. So that's on a 4-cylinder engine. I've got a run up. So going from idle to 5,000 RPM, and we've got X, Y, and Z vibrations, right, in G here that we recorded. So again, I've got a test splitter. This one isolates the X, Y, and Z vibration signals, and that's where I'm using my waterfall analysis. So let me run the process first of all. So you can tell it's very fast. Let's have a quick look at the properties before looking at the displays. I think it's important to understand better the displays later on. So I'm producing amplitude spectra. That's the modulus of the FFT, not PSDs. You know, depending on the culture in your company, some people prefer PSDs, others prefer amplitude. So this is in G squared per hertz typically. This is in G RMS typically. So that's where you scale the amplitudes. Here I've got all the properties typical of the FFT algorithm. So we've got Hanning weighting function. The buffer size is 4,096 points. The buffers are overlapped by 67%, and they are averaged, linearly averaged, and not peak hole, right? So that's very typical. Well, the most important thing is probably the buffer size here. And then we want to consider the minimum speed to be the minimum. That's a keyword. That's what we call a metadata. So it's going to look at the speed channel and look at what the mean value is of that channel. Similarly, for the maximum speed, it'll do that automatically for you by default. And how many spectra do you want? So 100 spectra. So here, if we go from 1,000 RPM to 5,000 RPM, so the range is 4,000 with 100 spectra. Each spectra will be, you know, there's going to be one spectra every 40 RPM, if I'm right. And for each of these spectra, I'm going to use 3 buffers that are going to be averaged and overlaid by 67%, right? So that's the most important properties, I would say. It's worth noting that the first one, increment method, by default it stays on PSDs, on speed, sorry. It requires the second input here that gives it the RPM profile. But if you want to do a time frequency analysis and not an RPM frequency analysis, you could choose X-axis simply. So that's a time. So every 10 seconds, say you'll end up with a spectrum. And the speed by buffer, this means, or say this is used when you've got a non-monotonically varying speed. In other words, not only run-ups or coast-downs, but you've got fluctuating speeds. So you want to use a speed by buffer. So it finds in the speed signal all the sections where the speed is between 3,000 and 3,100, say, extracts all the signals and combines them together and does the analysis. So, but basically, it works for both, monotonic speed profiles or fluctuating speeds, and that's driven by this property here. So, stop with the theory now. Sorry about this. Let's have a look at this very colorful plot here. That's the waterfall plot for the x-axis. We've got the same for the y-axis and the z-axis. So what we see here are those lines here. So in practice, you can tell it's just the concatenation of spectra that are put in this plot here. So it's not necessarily very readable or what. So sometimes it's preferable to go for the surface display, and I personally like the top view. Now the problem is that we don't necessarily see well those other lines, so you may want to choose to go for Z logarithmic axis. So that makes it sometimes clearer. Let me zoom in the low frequency range now, so below 500, say. So now you have to go into the properties, and you've got a limits here. So by default, it goes on auto. Here, I want to say no, go to 500. Look at this, very nice. That's my waterfall spectrum, and we see indeed those diagonals here, if you like, those lines. So I can track them using an order cursor. If you maintain your mouse on this button here, you've got this order cursor here. And you can look, if you see on the top left of the waterfall, you see a little yellow post-it. It says order 2. And then we move on to the next noticeable order, and that's order 4. And let's move on to the next one. That's 6, right? So now it's very nice. I'd like to extract the slices. Those slices, you know, the slices corresponds to order 2, order 4, order 6. So we can do that within the waterfall display. So if you go in the properties and the advanced, you got this show slice display here. And so it adds basically a new display to your screen. And now if you go back, so now we've got 2 toolbars, one corresponding to the waterfall display and another one corresponding to this slice display. And you can switch between the two with those buttons here. So let's go back to the toolbar corresponding to the waterfall display. And let me choose an order cursor. And every time I click, I get a display of the order slice below. So here I've got 3 order slices, order 2, order 4, or order almost 6. But you can also enter it manually with this button. So here you've got order, semicolon, and comma separated values for the order values. So let me just type it exactly 2, 4, and 6. Right, so that's 2, 4, and 6 now. That's very useful when you're trying to find which are the dominant orders. A quick view. However, be aware that you might want to use another tool for extracting the orders. I'm going to show it in a minute because this one has limitations. First, it doesn't have the overall capability here. But mostly, you know, it's got, you know, it's doing it in a very crude manner, in a very you know, fast and crude manner. It's simply looking throughout this line, and it's looking for the points that fall exactly on this line. There's no bandwidth around this line, so that's why it's very noisy. Again, it's a way to quickly assess what are the big orders in there, know which one you want to extract. But I wouldn't use it for your report, you know, showing the various orders. I'll show you how to do that later. Then we've got this Campbell plot. Let me just open this up. So this one shows me, I've zoomed it already. Yeah, so the axes are flipped here. So we've got speed now in X, and the y-axis represents the frequency. Some of you might prefer to represent that this way. By the way, the waterfall display can be rotated as well, such that it appears with those, you know, the axis in this direction. Anyways, here we see those circles as opposed to a nice contour plot of colors. And the nice thing with Campbell plots is since you know it's less packed with pixels, colored pixels, we could compare. So if I choose 3 plots here, we could compare the waterfalls, if you like, or the Campbells of the 3 axes. That's something we can't do with a color map. I hope you appreciate that. You know, it would be very, very difficult to read and impossible to plot, really. But anyways, here we see that the second, well, I think it's the second order. Let me see. If I go in the properties, speed, frequency, order lines, here we've got order lines. Let me just type 2, 4, 6 in there. Show labels, solid. Yeah, let me do apply. Apply is really nice because it doesn't close your window, your property window, right? So here we clearly see order 2 in this black line, and 4 and 6. So it's another way of representing the data. It's got its advantages and its limitation. It's up to you to choose which one you want, which one you prefer, right? So those 2 plots display the same thing. Now, well, I'm really interested in extracting those slices that I guess most of you are interested in this plot here, and I told you this plot is fairly limited. So what we have, if I go in the rotating machinery palette, is this complex frequency manipulation glyph. So let me drag this one in. Let me connect this one like that and double click on it. So you've got several options here. What I want to do is extract an order slice, say order number 2. And the nice thing is it provides you with further options to define a bandwidth around that order line. So it can be a constant frequency around or constant a fraction of an order. So let's go for order, and the order bandwidth will be, I don't know, node 2, for instance. And then, it'll sum all the data around that, that it finds within this bandwidth. And then I can display that. So I'm getting 3 there. That's for order 2 for X, order 2 for Y, order 2 for Z. So I want just the order 2 corresponding to what I had here. Order 2 is in red. X, that was X, sorry. So here you can tell it's less noisy. It's a smooth type order line. And then what I would typically do is copy and paste. So you can do copy and Control C, Control V, or right click and duplicate this one. So what I would typically do is this, and now ask for order 4. And again, duplicate that and ask now for the overall. So in order to get the overall, you go into the properties. It's not an order. It's the sum to 2D. So the whole spectrum will be summed in the direction of my mouse and represented as the total energy summed versus the speed in RPM. So if you click on sum to 2D, the 2D view will be the y-axis, the speed. So you have to change that as well. So we've got order 2, order 4, overall. Now I want to overlay all of them. So you go into XY display and the advanced. And what you want to do is ask for, it's below, it's 3 inputs or how many inputs you want. And there you've got means to display all those 3 spectra. You have to tell it, I want 3 slots in there. And either you go into properties or and then select which channels are displayed, or you run it again. And if I display that with the log axis, what I'm going to do, I'm going to add order 6 because I know it's fairly strong. Up, so 6. You see how fast it is, and the idea is then you can save it and reuse the next day with the new data that's coming up, or you can drag in there not 1 test but 10 tests and rerun it, right? So now I want 4 slots. And let me just see. Well, here you've got your overall in green on the top and the various orders, order 2, order 4, order 6 with a color code. All this been obtained with summation around, with a given bandwidth around an order line. So it gives you fairly smooth and quite accurate order lines. Now, once you've built that, you can continue creating a sophisticated process workflow like that. And if I move now to the next tab here, I've got a very similar analysis, but this time with a report. So this report can be built, with your mouse very, very easily. Right-click, insert. But let me first run it. So here we've got our waterfall analysis, and in this superglyph, I've hidden, if you like, the complexity of the order extraction. So this one contains the various complex frequency manipulation. it's very easy to create a superglyph. You select the glyphs you're interested in turning into a superglyph, and you click here, replace selection with superglyph. And then once you've created it, you can save it into your palette here anywhere. So on the rotating machinery, I could have saved my glyph with my icon, and it could have been called something like order extraction. And so the result is this. I've got my report now for X, Y, and Z. So what we have below is the order extractions. I think I used 2, 4, and 6, and I put also reference line. You could have thresholds. You know, you could have spectra that you know that they shouldn't be exceeded, for instance. So you can enter such a reference line by entering the coordinates of various points, and it draws a line through them. You can have different reference lines like that. But the nice, interesting bit is like you build it, you know, with your mouse. You right-click and you say insert, whatever plots, a waterfall display or whatever, and it creates as many inputs as there are plots, you know. And then you just connect it, and you end up with your nice report with your logo, your name, etc., etc. I could add, for instance, I don't know, we could add, you know, the overall level in RMS. That's very simple. You add a text box, and in there you add the keyword corresponding to the overall RMS. It exists in those pipes. So I won't show it here because I'm afraid we're running out of time here. But basically, you can then export this report, and basically you've got your workflow now ready to go. You know, you've picked the buffer size you want. You've extracted your orders and displayed them together with the overall, and all this ends up in a nice report. So I guess that's the end of the movie here, and a happy ending with a report. I hope you learned something, and I hope you have questions. I'm here to try and answer your questions. So thank you very much for attending. You've got the Q&A or the chat panel to ask questions now. Thank you. So I've got a few questions here coming in the Q&A. I'm going to start with the first one. What is a practical example of nonlinear Campbell plot? Well, that's where, let me just move to the, yeah, it's not represented here, but say you had circles around this, what color is that, yellow dashed line. So that typically means that at a high speed, you've got a stiffening of your components. Take a blade, for instance. It doesn't behave the same at low speed and at very high speed. It stiffens, and it has all sorts of you know, phenomena occurring to do with its characteristics. So that happens sometimes. You know, at high speed, you've got it may heat up. It may, you know, if you get oil in there, if you get a specific material that stiffens or softens or things like that. That's a typical use case of nonlinear orders. So I've got another question about fluctuating RPM data. I hope I answered this one. So indeed, we're capable of accounting for run-ups or coast downs, so monotonic type RPM profiles. If you're not in this situation, but you've got a fluctuating speed, that's where you need to use the property, I think it's analysis type and speed by buffer in the waterfall analysis. I'll let you try that and come back with me with any question you have on the practical use of that. My email address is here. It should be straightforward, but in case you've got questions, just drop me an email. So I've got another question. Someone's having his RPM or her RPM data available through the CAN network of the data. So we read a number of file formats in the software. Not only the file format of the classical, analog data acquisition systems such as HBM, our hardware or other hardware systems, but we also read files coming from the CAN and with vector, for instance, or IPtronic. We natively read those files. So if you're using vector, IPtronic, or others, reading CAN directly, getting hold of the CAN information and creating a file, chances are that we can read this file. If the data is not equally sampled, we've got means to resample that at a fixed sample rate. And then there you go. You can associate that with analog data coming from your accelerometers. No problem at all. So another question that's linked to what I just said. Indeed, if the input data is not evenly sampled, this software requires, since everything's based on FFT, this software requires a constant sample rate. So we've got means to resample data. The most sophisticated one is probably to use spline functions through the data and sample basically the spline at a given rate, so many thousand sample per second, right? So indeed, we require evenly spaced data, but if in case you don't have, we've got plenty of means to resample that. No worries. Again, let us know if you need any help with that. So I've got several questions to do with the software. Let me fire up the software again. One question is, once you've created your superglyph, how can you save it into the palette? So let me just show it to you. Let's do it. I'm selecting all those glyphs. I'm clicking on this button. That creates my superglyph. There are means to make sure you've got only one yellow. I won't enter into this level of details. But once you've got your superglyph, first you still access it. You still can access that, right? And it's in the properties. But in terms of saving it, you just right-click, save as. Where in the palette do you want to save it? So let's go under rotating machinery. What name do you want to give it? Let's call it order extract. Some information. You may choose another icon. It's pointing to a specific directory that you can see here, but you can change that and use Paint or whatever fancy software to create those little icons. And when you click on OK, there you are. It's here, and you can reuse it over and over again. Someone else tells me this VibeSys thing looks extremely similar to GlyphWorks. I wonder what the difference is with GlyphWorks. Well, the two main differences are in the palette of glyphs. In GlyphWorks, you have fatigue. You've got all sorts of other palettes that we don't want to have here if we're interested only in vibration and acoustics. So the glyphs are simply positioned in a more, hopefully, an easier to find type sets of palettes. Another big difference is if you go into the help, you've got worked examples, etc., that are really dedicated to VibeSys. So we've got worked examples here in VibeSys that teach you how to do model analysis, acoustic metrics, data cleaning, things like that, right? Quality analysis, comfort, things like that. So yeah, it's dedicated really to noise and vibe analysis. So, but indeed, it looks extremely similar to GlyphWorks. Let me see if there are other questions that I haven't answered. So a question that relates to a previous one. So, you know, data coming from different systems. Say this one's coming from the data acquisition system, and this other one's coming from the CAN. You know, you can use your waterfall analysis. Let me just copy and paste that. Say in there you've got the RPM. It goes there and into the speed. This one's got the analog data. You know, there's no problem in doing that. Maybe it needs some resynchronization, so we may want to change the base time, and we can do that within VibeSys or GlyphWorks with metadata. So, but you know, we've always find a fairly easy mean to gather data from different acquisition systems. That's not a problem as long as we read the file format. And if we don't, we've got this. Where is it? Under applications, I think we've got the ASCII translate. So if you get it under the form of a text file, we can import it, and then there is no problem. And the report, can we export the report to Word? Yes, we can export it to a series of different formats, like to a picture, BMP file, or JPEG or something, Word. The nice one is a PowerPoint. So here we'd end up with 3 slides, one for X, one for Y, one for Z. So we've got different ways, a PDF also, PDF documents. So yes, this can be exported, and this can be automated. You know, once you run the flow, it does the export. We've got options, properties to do with the naming of the exports. So I think it's 5:10. I think it's good time probably to stop here. Thank you everyone for attending, for the number of questions I got. That's very nice, you know, to know that people seem interested when they ask questions. So thank you again, and feel free to drop me an email if you get additional questions, or if by any chance, by mistake, I forgot to answer your question. Just send me an email. Thanks.